his aura. Professor C.R. Rao, a renowned personality, accomplished academician, a patriot to core, is a recipient of numerous prestigious awards, both nationally and internationally. Shanti Swarup Bhatnagar Award, National Medal of Science, USA, to name a few. He has mentored numerous students. Many of them are now on the path of their guru, legends in the making. We are fortunate to have one of his illustrious student, Professor G.S. Rao, Distinguished Professor, University of California, as a inaugural speaker for this international FDP. We were thinking of having something very memorable to celebrate the birth centenary celebrations of Professor C.R. Rao. The thought of organizing an international FDP came to us so as to inspire the faculty, in turn the students, to be on the path shown by Professor C.R. Rao Garu. We were trying to identify who would be an apt person. Professor J.S. Rao came to our mind as who could have been better than him, who is keeping the mantle of Professor C.R. Rao burning bright with his dedication, his price, and when I contacted him, he was very kind enough to accept our invitation to deliver a talk commemorating such a great occasion. Thus, this FDP took the shape. We had other eminent resource persons giving their acceptance to be a part of this 1 week international FDP, which is beginning today and will go on till 2nd January 2021. The inaugural address by Professor J.S. Rao on a few excursions into statistics is surely bound to take you all to the tour of world of statistics and will be a curtain raiser for the ones who are exploring the world of new possibilities with statistics. Followed by Dr. K.S.N. Murthy from Indian School of Business, who will take you all into the world of predictive analytics on the 2nd day. We have with us Dr. M. Venugopal Rao Garu, a data scientist at Midovo, IO, on the 3rd day to take you all on a tour into the world of data science and prepare you for the careers in it. You will all be taken into the world of deep learning by Mr. KVCH Madhusudan Rao Garu, Manager Analytics, Kerner Health Center, on the 4th day. Dr. Vishnuvardhan Garu from Pondicherry University will enlighten you all on statistician data doctor on the 5th day. And on the final day of this inspiring international FDP, you will be taken into the world of optimization techniques by Dr. A.K. Malik from BITS Pilani. I'm sure you will have a lot of takeovers and learning from this FDP, if one of its kind, a true gift to the living legend, Professor C.R. Rao Garu, on his birth centenary. Welcome you all to this international FDP. It's indeed my proud privilege to give an introduction of the dynamic and dedicated Department of Mathematics and Statistics, RBVR, Reddy Women's College, to you all. The Department of Mathematics is one of the oldest departments, which is established in the year 1962 with introduction of PUC. BSc Mathematics was started in the year 1965 and BSc Statistics in 1995 and MSc Mathematics started in the year 2005. The major milestones of the departments are establishment of Statistics Lab in the year 2000 and establishment of Mathematics Lab and introduction of practicals in 2005. The department have 13 faculty members, out of which 2 are PhD holders and 1 set and 3 faculty members are pursuing their PhD. The department has well-experienced, knowledgeable and dedicated team of teachers who has a vast experience and are well known for their expertise. The faculty members on the academic boards, examiners of paper setters for varied universities and other autonomous colleges and universities. Our department has quite a few distinctions, like we are the first in the state to introduced Mathematica software as a part of practicals for mathematics students and Minitab for statistics students. We are the first in the college to introduce student projects for BSc and MSc final year students. And we are first in the college to succeed in collaborating with premier national institutes like IIG, Indian Institute of Geomagnetism, Navi Mumbai, and National Geophysical Research Institute for the student projects and summer internships. The department helped the students in doing the statistics projects using primary data. Our department has completed, 5 of our faculty members have completed UGC minor research projects. Our faculty members bagged 3 first prizes in poster presentation and conducted by the Indian Science Congress Association, Hyderabad chapter. We are associated with the school for differently able children, Manasa, under institutional social responsibility. And the department adopts varied student-centric methods like heuristic method, experimental method, participative method, ICT method, etc., so as to make the learning effective and fun for the students. The department uses varied information and communicative technology tools like Google Classroom, Zoom app, etc., which has come as a big boon in the social distancing and lockdown time, which has helped the teachers to make online classes and interact with the students. The department has contributed to the research and has undertaken varied academic extension activities. The department is known for varied academic and extension activities it undertakes. Some of these are seminars, FDPs, distinguished lecture series, advanced lecture series, National Mathematics Day celebrations, Ganana every year. Max and Stats Club, Ganana has been established to promote mathematics as an interesting and fun to learn subject. Our students are well placed, are accepted by the industry, which have been placed in various corporates and in institutions like Wipro, Genpact, Concentric, Tata Business Support, etc. They have shown their acumen by winning a lot of prizes at varied events. Lot of activities are undertaken by the department to support the student learning and growth. Varied practices have been adopted to make teaching learning effective. Let me take this opportunity to welcome today's resource person, Professor G.S. Rao Garu. At the outset, let me acknowledge the kind acceptance by the esteemed speaker, Professor Srinivasa Rao Jamala Madaka Garu, popularly known as Professor J.S. Rao Garu, for immediately agreeing to ignite this curiosity by sharing his expertise, experience, and knowledge for the benefit of the academic community, in spite of the tough times and his hectic schedules. Let me have the honor of introducing the inaugural speaker of the International FDP, Professor J.S. Rao Garu, a legend himself, distinguished professor, University of California, Santa Barbara, USA, who has very kind enough to accept our invitation to be the inaugural speaker for this International FDP, which shows his inherent nature of being very ever ready to help the academic world. Today is a historic day for our institution, especially the Department of Mathematics and Statistics, as it matters us more to have Professor J.S. Rao Garu to be as inaugural speaker for this international event, which is being organized by us to commemorate the birth centenary celebrations of living legend, Professor C.R. Rao Garu. As Professor J.S. Rao, a legend himself, is a direct student of Professor C.R. Rao Garu, and he is an embodiment of the knowledge and personal traits of Professor C.R. Rao Garu. In 2019, Professor J.S. Rao was awarded the C.R. Rao Lifetime Achievement Award by the Indian Society for Probability and Statistics. Professor J.S. Rao Garu has done his Bachelor of Science and Master of Science and PhD from the Indian Statistical Institute, Calcutta, India. Professor J.S. Rowe is among the leading researchers in statistical science over the past 5 decades, especially in areas like directional statistics and goodness of fit testing. Is the author of 3 books and close to 200 publications. Professor J.S. Rao started his academic career at the India Institute, University, USA, before joining University of California, Santa Barbara in 1976, where he is now a distinguished professor. He is the founder of the Department of Statistics and Applied Probability at the University of California, Santa Barbara, and led the department from 1989 to 1993. Professor J.S. Rao achieved international recognition for pioneering work in developing new tools to analyze nonlinear phenomena like directions and circularity. He has been visiting positions at many universities around the globe, including in Australia, Sweden, UK, Germany, Thailand, Italy, Hungary, Malaysia, as well as in India, where he currently holds a distinguished visiting professor appointment at Geetham, Vishakhapatnam. Professor J.S. Rao received various prestigious and renowned awards and recognitions for his pioneering contribution to statistical theory and applications. He has been elected a fellow of the American Statistical Association, the Institute of Mathematical Statistics, the Institute of Combinatorics and its applications, and an elected member of the International Statistical Institute. He has been awarded an honorary doctorate by the Sweden University of Agricultural Sciences in 2014. Professor J.S. Rao has been honored with Outstanding Graduate Mentor Award by the University of California in 2017 in partial recognition of the fact that he supervised 45 PhD students by then who are working as academicians and as statistical practitioners in various organizations all over the world. He has been an invited speaker at more than 300 national and international statistical meetings all over the world on topics including problems on weak convergence, directional data, and non-parametric statistics. He has been a member of the editorial boards of many leading journals, including Statistics and Probability Letters, Stochastic Modeling and Applications, the Journal of American Statistical Association, and the Journal of Non-Parametric Statistics. We are fortunate that he has readily accepted our invite to be inaugural speaker for this international FDP to share his knowledge, expertise, and experience. I'm sure today you will be all inspired into the world of statistics by hearing from a legend, great researcher with a passion to make a difference in this world by his research. I now leave the session to Professor J.S. Rao Garu to take over and share his expertise, experience with all of us. Over to you, sir. Thank you.
Thank you, Shweta. You guys can hear me now? You can, right? Am I audible to all you guys?
Yes, sir.
Okay, good. Just want to be sure. Okay, thank you, Shweta, for this nice introduction, and thanks for the invitation. I'm very, very happy to participate in this faculty development program. It's a wonderful idea to introduce faculty to refresh their memories about some topics. And I think I'll try and give you a broad brush idea about statistics and what I do. And I'll start by showing you some slides. And this is what I'm going to show you as my first slide. And let's see, where do I now show this? This is something that I always get into issues of. Let's see, where is my
your bottom share screen is in
bottom? Okay, this one here, huh? Share screen. Okay, do you see this one? Do you see my picture at this point? Do you see the picture that I'm showing you, a black and white photo? Hello? 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 Okay, let's see. Let's start at the beginning. I'm going to, where are my controls here? Okay, now this is no good. Let's see. Let's get this going correctly. Now, let's see, share screen. And this is the picture I wanted to share. Do you see my screen now with a black and white photo? Someone say yes. Yeah? Hello? Hello, hello. Do you see this picture I'm trying to show you? Let's start at the, okay. Participants mute, resume share. Okay. Do one of you, can one of you tell me that you can see a black and white photo I'm showing you? Hello? Hello?
Hello, sir. We can
Hello,
hear
yeah? You can hear us and you can see my screen? Can you see see the picture I'm showing you? Okay, let me start at the beginning. Okay, now I think I'll get going straight to the talk. If you don't see this picture I'm showing you, that's surprising to me. Can anyone say yes? No? Okay, okay. I'm going to get going on the talk itself then at this point. Share screen, go to my talk. Okay, do you get to see my screen now?
Yes, sir.
Okay, okay, I'm glad. Were you able to see my black and white picture I was showing you earlier? Maybe not. Anyways, okay, you see the screen that says my name and my affiliation, right? I'll keep talking once someone says yes. You can see my screen, right? That says statistics, some excursions.
Yes, sir. We can see.
Okay,
Sir.
good, good, wonderful, wonderful. I'm going to go on with this, and if I have time at the end, I might show you. Okay, as usual in India, I was known J.S. Rao. Jamala Madaka is my family name, so that's what I write in Andhra in the first place, and then Srinivasa Rao. But as I immigrated to USA, they put the family name at the end. So my name is Srinivasa Rao Jamala Madaka. People call me Dr. J and Professor J and so on. Anyway, I started this Department of Statistics and Applied Probability in Santa Barbara. And I'm going to tell you a little bit what I call statistics, some excursions. Okay. Statistics is the science of dealing with collection, summarization, analysis, and interpretation of data. As a brief description of what statisticians do, is the science, or if you like, an art of dealing with the collection of data, summarization of data, analysis and interpretation of data. Collection, you see, each of these is a specialized topic in statistics. Collecting data, we have a topic called sample surveys, sampling techniques. How do you draw a random sample from a population? And there is a topic called design of experiments. How do you collect data on a planned experiment? For example, for comparing, certain drugs or maybe certain varieties of wheat. So on. Collection is one of the aspects of statistics. Summarization of data. We do that through graphical summaries as well as through various other tools that we use. There's something we call sufficient statistics. Of dealing with, say, in some cases, like when you are dealing with data from a Gaussian or normal distribution, bell-shaped curve, it turns out instead of dealing with all the data, you can deal with only two numbers, the sample mean and the sample variance. And they contain all the information relevant for inference. And those are what we call sufficient statistics. So summarization can be graphical or mathematical and so on. Analysis and interpretation of data. That's what we call inference, statistical inference. I'll go on and say some more about this inference aspect. Inference is to draw conclusions about the population, their entirety, after having observed only a subset of it, a sample. Statistical inference, being the art of generalizing from sample to population, is the bridge for most scientific discoveries. See, we are the background, people for all scientific discoveries. Even in the so-called God particle that they discovered recently on CERN in Switzerland, CERN, it turns out that it was statistical ideas that finally they lead to their conclusion that there is such a particle. Okay, let's see. I'm going to show you. Well, am I going up too fast? Okay. This is a famous quote from P.C. Mahalanobis. The first slide I was trying to show you, maybe I'll get a chance at the very end, contained P.C. Mahalanobis. Mahalanobis is the founder of the Indian Statistical Institute in Calcutta, where C.R. Rao was a researcher and a professor and developed his career at the ISI Calcutta, Indian Statistical Institute. Mahalanobis was fond of saying, statistics is the key technology of the current day. Statistics is the key technology of the current day. Someone already mentioned statistics helps develop ideas in science and in generalizing what you see in a sample to the population. Is not a science by itself. What's the difference between a science and a technology? A science is to discover nature, find out principles of nature like physics or chemistry. And on the other hand, technology like engineering is one where we use scientific ideas to help mankind. Very, very broad sense. That's what engineers do. They produce a better car, better cell phone. So that's what statisticians do. They develop better theories from on different scientific, using various scientific ideas like mathematics and so on. Life is the art of drawing sufficient conclusions from insufficient premises. I'm just giving you some interesting quotes about how important we are as statistical thinking is we draw sufficient conclusions from insufficient premises. Statistical thinking will one day be as necessary for efficient citizenship as the ability to read and write. And that day has already come. We are at a place where statistics is all around us. So, opinion polls and advertisements and so on. And so on. So it's as necessary for efficient citizenship as the ability to read and write. That's what H.G. Wells said. I give you some quick examples of statistical modeling or stochastic modeling. And someone says there is a 60% chance of rain tomorrow. It's based on predictive modeling. It's a very deep idea. How does this one conclude there's a 60% chance on what factors, what data? So I'm just going to throw you some of these ideas, not get into any detail, because that will be a course by itself on how they do this. The dam is built to withstand a 100-year flood. A dam for a river or something is built to withstand a 100-year flood. And what does that mean? In engineering, signals are contaminated by random noise using error correcting codes. And these are what we use in modems and CD players. You may not realize that there are these codes used to transmit information with least errors. In operations research, queuing models, inventory models, reliability of systems. This is a topic, a big topic by itself, operations research. It used to be a hot topic. I don't know if it is still taught in India these days as a separate topic. So these are all different things, reliability, inventory, how many stock should you keep so that you don't overload yourself, but on the other hand, you don't run short on orders or an item. So inventory models, queuing models, and so on. So these are all some of the examples of, in biology, models for the spread of epidemics. For example, AIDS, H1N1, now COVID-19. How does it transmit? How fast does it transmit? How do we achieve what we call herd immunity? And how many people should you vaccinate in order to protect the rest of them even? This is called herd immunity. Growth models for human and animal populations. Growth models, this will be as simple an idea as a baby growing from week to week. We measure his or her weight, height, and so on, and chart it. Growth models. There are some statistical tools in multivariate analysis to study growth models. Theory of evolution is a mixture of chance events, mutations, and so on. So these are all, this last topic is a part of genetics. In physics, which we think of as something very theoretical and solid, there are these, very many ideas of statistics that go in there. Bose-Einstein statistics. It's unfortunate I couldn't show you the first slide. I was going to show you a picture of Bose. Bose was one of the people at the Indian Statistical Institute in those days. Satyendranath Bose is Bose-Einstein statistics, and also the Higgs boson particle. Higgs boson is the name for what they call the God particle. In any case, Maxwell-Boltzmann theories, they're all about in quantum mechanics, interacting particle systems, percolation processes, Brownian motion. These are all ideas that connect to physics, but they have their bearing in probability and statistics. And deliberate introduction of chance. We deliberately introduce randomness into our experiments. This is in order to draw a random sample, or in design of experiments, we assign units on which we experiment to the different treatments at random. So we introduce randomness deliberately to get representation of the sample representing the population. Monte Carlo methods, simulations, these are what we do. I'm sure most of you do this, probabilistic algorithms to simulate and to model complex data sets. This is where, statistical inference being inductive involves logic and philosophy, and hence open to possibly different interpretations. Let me pause here for a minute. Statistical inference is inductive. What does inductive mean? Logic or philosophy inferences can be of two types, deductive or inductive. Deductive is to have a general principle and then say it applies to various, special cases. Like, for example, I tell you a plus b whole square is a square plus b square plus 2ab. It applies to any a, any b with equal vigor, no errors. On the other hand, statistical inference is inductive. Inductive is when you see certain subset of the entirety, but then you want to say something about the entirety based on what you saw. This is called inductive inference, from small subset to the entirety, from sample to the population. And it's called inductive inference philosophy, and it depends, and there are different interpretations. The same data, one can conclude, make inferences of different kinds, and then people can argue about who is right. And this has been in statistics. There are those classical statistics, Bayes arguments that come into play, and so on. Let me throw in a simple example for you. You toss the coin 10 times. Suppose we see 9 heads out of these 10 tosses. 9 heads out of these 10 tosses. What can one say about the outcome of the toss? Think for a minute. You toss a coin 10 times. You see 9 out of 10 heads. 9 out of the 10 tosses, 9 of the times it shows up heads, and only 1 time the tail. What can you say about the outcome of the next toss? This is called a prediction, in fact, predictive inference. And now it turns out there are, I was saying in my next slide that there are at least 3 possible answers for this question, and all are right. For example, if you're a good probabilist, you will say, this coin, what does it care what happened in the past? The coin is a fair coin made up by minted at the treasury or the government, and so it's a fair coin. So the next time the chance of heads and tails is the same as before, maybe 50-50. That's a correct answer. That's the probabilist answer. On the other hand, another answer is that you see 9 heads out of 10. Maybe this coin is not a fair coin. Maybe it's a loaded coin, loaded more in favor of the heads. And so you might say, oh, it's more likely to be heads. You can actually come up with an answer for this. This is called a Bayesian argument. You learn from what you see in the past. Use the past data to say what might happen in the future. This is called a Bayesian prediction. And that says, given there are 9 heads out of first 10 tosses, maybe there's a much higher chance of heads in the next toss. It's not quite 9 out of 10, but something close to that. And then the third possible answer is, there is this thing that some of you will recollect. There is something that we call the law of large numbers that says, eventually, if this is a fair coin, you will end up getting more tails at this point. You have already seen 9 heads, so is more higher chance for tails because the coin is supposed to even out. And so that says, this is typical of, you perhaps heard of several families that say, oh, we have had 3 boys, so the next one is going to be a girl. Well, how do they know? This is called a gambler's fallacy. Gamblers say, oh, I've been losing money all these last $4 I put in, so I'm going to win this time. So we keep playing until their pockets are empty. And here is a thought. A doctor comforting his patient, he says to the patient that you have a serious disease. Of the 10 people who get this disease, only 1 usually survives. But don't worry, it's lucky you came to me because I've recently operated on 9 patients with this disease and they all died of it. So very comforting for the doctor to say, I operated on 9 of the, the last 9 patients have died, so you're lucky you're going to be surviving because 1 of the 10 usually survives. Okay, this is called gambler's fallacy. So what was the third logic? Third one says higher probability for tails. And Bayesian logic said higher probability for heads. And the probabilist said it'll be same as before, 50-50. So I'm saying this is a matter of logic and philosophy that is involved in statistical inferences and predictions. And data quality and scrutiny. It's called, does anyone recognize what GIGO stands for? Garbage in, garbage out. Garbage in, you put data that is, not correctly collected or whatever, then your conclusions will be also garbage out. Faking of data. You heard of these big names, Mendel, Newton, Galileo, Dalton. They all apparently manipulated data to some extent. How do people know that Mendel, Mendel, for example, he was doing genetic experiments and he was supposed to get certain proportion of certain, types of proportions, 1, 4, 4, 1 or whatever. And his data was exactly 1, 4, 4, 1. And that is very unlikely to happen. So I think what people say historically, even big names like this have fake data sometimes. Before analysis, you should ask questions like, how are the data ascertained and recorded? Are the data free from measurement and recording errors? Are the concepts and definitions associated with measurements well defined? These are very interesting concepts. For example, if I say family income, there are 2 big ideas behind here. Family, what does a family mean? How do you define a family? Is it a nuclear family? If your parents stay with you, is that a family income? Would their income included? What does income mean? What kind of income? So in fact, I'll tell you an anecdote. In 1960, when way back, and I joined the ISI Calcutta for my bachelor's in statistics degree, BStat, and the first thing we did was what was called a post-census survey. Post-census, every 10 years we have a census in India. Most countries do such censuses. And what the ISI was tasked, the ISI in my notations is the Indian Statistical Institute, it's asked to check how valid is the census data. It's called post-census surveys. And we as students were sent around various families with the data already collected to verify if the data was properly collected. So then the questions come up. What does family mean? What does family income mean? So this is what I mean by saying, are the concepts and definitions associated with measurements well defined? That's why you have to have a clear definition before you send out observers. Are there differences between observers? One observer might use one definition of family income and the other one might use a different definition. Are the data genuine, ascertained as stated, or faked, or edited, or adjusted? Are any observations discarded at the discretion of the observer? Some observer might think, oh, well, this data looks too big, too far out. So these are called outliers. And the question is, there are some books written on how do you define an outlier? And outliers meaning something that doesn't fit the general pattern of the rest of the data. How do you define that concept, that idea of outlier? And then it turns out outliers oftentimes lead to serendipity. You learn something new that you didn't expect. And that may lead to some new ideas and so on. So outliers are useful idea. These outliers have undue influence in statistical inference. Now, some of you, I'm sure, have done or taught regression methods, and there are outliers. 1 point in X, Y in a simple linear regression. If a Y value is very far out of the straight line that for the rest of the points, that pulls the whole straight line in one direction. So it turns out the outliers have a major role. What is the influence? And there are these concepts called influence functions for data. And I'm not here to tell you go deep into any of these concepts, but to throw ideas that these are interesting questions people should ask. How about the data? Are there outliers? What is the effective population for which the observed data provides information? Even the idea of what is the population. And is there any non-response, partial or complete, from selected units of the population under survey? See, non-response is a very important concept. Oftentimes you send out a survey questionnaire to 100 people, you only get 60 of them back. Let me repeat. You send out 100 questionnaires to 100 families, and you get only 60 of them back. And the 40 that didn't respond, they might have an important message. They didn't respond for a reason. So how do you deal with such non-response? And in surveys, this is an important concept. Are the data obtained from a homogeneous or a mixture of populations? One of my students recently did a paper on the following topic. If you look at the heights of human beings, women's average height is slightly less than the men's average height. In other words, there are two groups. It's a bimodal distribution, the height distribution for humans. There will be a peak at 5 feet, different countries might be different, at 5 feet 6 inches, and the peak at 5 feet 9 inches, one corresponding to women, one corresponding to men. So it's a mixture of populations. So if you recognize that, then there may be other methods of dealing with this problem, mixtures of distributions. Is there any prior information on the problem under investigation or on the nature of observed data? Now, this is very important. Prior information, that's a heavy word. That's what people use in Bayes methods. Bayes is a big name in statistical definitions. Bayes methods are those which say you have unknown parameters that you want to estimate from a given sample, but then maybe you have some prior information about this parameter, prior information, even before you collected the data. Like, for example, think of a binomial proportion P. P goes from 0 to 1. P may be the proportion of defectives in a box of nails that you buy. And you know from past experience, you have been buying these boxes of nails, and the proportion of defective nails, whatever your definition of defective is, maybe there's no more than 1%. So you already know this proportion of defectives is no more than 1%. So why assume this P is on 0 to 1? Right? It doesn't make sense. So maybe you should somehow input this proportion of defectives, the prior information, into your estimation of the proportion of defectives. So that's called Bayes estimates and so on. So, okay, there is someone who said the government is very keen on amassing statistics. They collect them, add them, raise them to the nth power. Nth power is the take the cube root and prepare wonderful diagrams. But you must never forget that every one of these figures comes in the first instance from the village watchman who puts down what he damn pleases. So that is what one has to watch for in statistics: garbage in, garbage out. So you need to watch out what you are getting, editing data, making sure what you are collecting is what you wanted to collect. Things like this are very important ideas before you actually do, big mathematical inference. Okay, statistical questions and issues. I'll just mention some of those that people usually deal with. How much wheat is expected to be produced this season? We used to do something called a crop cutting surveys. The Indian Statistical Institute, as students, we were sent to a place called Giridih, and then did a survey how to estimate how much wheat is going to come in this season in this 10 acres of land. So you cut a small piece of land, harvest, and then estimate. So crop cutting surveys are used in order to decide how much is going to be expected, how much is going to come this season. And then why would you do this? Because then depending on this, you might be able to import or export and so on. That smoking causes lung cancer. Does an aspirin a day keep the heart attack away? Is a particular newly discovered poem written by Shakespeare or one of his contemporaries. This is a very interesting topic. I have had a student who worked on this thesis. If I give you, if you find a new poem, is it written by a particular author? How do you tell that? That's called text analysis, semantic, latent semantics, and so on. Anyway, this is about, one of my students did the following topic. Suppose a professor gives an essay to be written on a certain topic in statistics, and the student produces a beautiful essay. Can you say how similar this essay is to something that's on Google? Somewhere you may have copied from online. So how do you find similarities between two texts? And more recently, I wrote a paper on the topic of stock markets, prices of stocks. You have a portfolios of stocks, say 10 stocks. How do you predict how the 10 stocks will behave, how the portfolio performs over time? You might think of this as a multivariate time series, multiple stocks over time. But then you can also, one of my papers is about, can you look at the Twitter data, what people are saying about these stocks? What is the opinion expressed by various people about these 10 stocks? Can you input that into your potential forecast? Because if a lot of people are negative about these stocks, one or two of them, then maybe they won't grow as much as your time series tells you, because time series is looking at the past data. And so we looked at how to incorporate Twitter data or something on, there are a lot of financial resources Can you look at those resources in terms of text and then see what those texts or Twitter feeds are saying about these stocks, and then use them to predict, to forecast your stocks? You can do that. Is there an optimal time of day to take a specific medicine? This is something very interesting. This is, this is called chronotherapy. Chrono means time-based. I will have an occasion to mention briefly something about this later on. This is a time of day is 24-hour cycle. Should you take a certain heart attack, heart medicine, for example, in the early morning or late night? What's a good time for taking a medicine? And if if a woman has to undergo a surgery, what part of the menstrual cycle is a good time for this surgery to take place? Those are interesting topics. These are called chronotherapy, chronobiology, and this is an interesting topic. Is the last born child smarter than the firstborn? Interesting question. In fact, I might mention here that Professor C.R. Rao, about whom we are celebrating, Kalyamput Radhakrishna Rao, he was the 8th of 10 children. 8th child out of 10 children that his parents had. So perhaps, I don't know, the answers to these questions are complex. Is the woman's claim that a particular person is the father of her child correct? DNA analysis. Is the selected jury for a particular trial representative of the overall population in the community? Now, you may not be familiar with this idea. In America, we select a jury of people from the town where the trial is taking place for a particular crime or whatever. This jury is supposed to be a representative jury for the community. And we select 11 such people, and they listen to the whole case, and they make a decision whether this crime was committed or not. So the question often comes up, is the selected jury representative of the overall population? How do you judge? These are all very, very deep questions. I'm raising questions to you, but I'm telling you how important statistics is in every aspect of life. Does the newly excavated skull belong to a man or a woman? What combination of factors provides the best possible yield? If you're trying to, is one of these things we teach in design of experiments. You have nitrogen, phosphorus, and something potassium. Combination of these three may be making a fertilizer. What combination is the best combination, and so on. Statistical quality control, that's a big topic by itself. And so these are all interesting areas. Now, I'm going to deliver what I promised you, the excursions. I'm going to bring up statistical ideas that make a difference. I'll tell you 4 different examples, very simple examples, where interestingly, something unexpected is what statistics tells you is the right thing to do, better thing to do. Okay, that's what I call excursions. 2 objects are there. Okay, here is as simple as I can make it. There are 2 things, like a pen and a pencil, with true weights, θ1, θ2, which are unknown. In statistics, we use Greek letters for the unknown parameters. The true weight, true is important word here. The true weight of an object is unknown to me, θ1, let's say. And then I know each measurement costs me $100, say, and there's a measurement error of E, a random quantity. See, what happens is when you measure the weight, what you are getting is not the actual weight. For example, someone might weigh something and says 1.5 grams. And someone else comes and says, no, it's not 1.5, it's 1.52. Yet another person might say it's 1.525. Okay, so in other words, the true weight is unknown. You are only trying to estimate it in some fashion. And there is a measurement error. Whatever measuring instrument you use, there's a measurement error. So what we get is the measurement error, let's call it E, I'm going to introduce some notations. Average of E is 0. Usually the measurement error can be plus or on the negative side or positive side. And the average of the error E is 0. Average of E square, which is called the variance of E, is, let's say, sigma square, a positive number. The variance is the average of the E squares. Okay, so that is, this is the standard models you were all familiar with. Namely, there is a measurement. This is how the method is. I take a measurement x1, one measurement on θ1. What does x1 consist of? There's the actual number that you got, 1.52. But there's the true value is θ1, and E1 is the error that went with it. So what are you going to say now? I'm going to say my x1 is the best guess. I spent my $100 taking the weight θ1, and I got x1. Although it has an error E1 with it, x1 is my best guess on θ1. So we declare θ1, estimated value of θ1. This is a, I don't know the audience, I'm sure you will know what hat there is. That's about estimate. Declare θ1 hat, estimated θ1, we put hat for an estimate. And we declare θ1 hat to be x1 and θ2 hat to be x2. What is the error that goes with θ1 hat, such an estimate? But θ1 hat is x1. What is the variance of x1? This is now constant, so variance of x1 is same as the variance of E1, which is sigma square. So it turns out variance of θ1 hat, which is the variance of x1, is sigma square. Variance of θ2 is sigma square. So you spent your $200, $100 for one measurement, $100 for the other measurement, $200, two measurements is all you got, and you got an estimate x1, x2 for θ1, θ2 with variances sigma square, sigma square. Variance of the first estimate is sigma square. Now, this is what anyone would do. If I gave you, maybe I give you a budget of $200, you can only take one measurement on each one. And that's it. That's what you take x1 and declare that to be θ1 value, and so on. Now, you know what? A cleverer statistical idea is here. A method 2. What I showed you is what I call a method 1. What is a method 2? I'm going to take θ1 plus θ2, total sum of the two weights, call it y1. How can I do that? I put both of them on one side of this, balance. And E3, error of measurement, is always this kind of error that I talked about. Its average value is 0, its variance is sigma square, measurement errors of that. So y1 is a θ1 plus θ2 plus error. And y2, take y2 to be the difference of the weights. Put them on two sides of the balance. And θ1 minus θ2 is what y2 represents. And there's an error that goes with it. Are you keeping up with me? I have method 1 where I measured one object, x1, second object, x2, done. The second method is where I take the sum of the two weights and the difference of the two weights, call it y1 and y2. How do I get my θ1 out of this now? It's a simple linear algebra, equations, two equations. If you add up y1 plus y2, θ2 cancels out. And then you get 2 θ1 and divide by 2. So that's my θ1 hat. I call it the double hat, the second estimate. See how I'm getting my estimate for the same object, first object, θ1, is the sum of the two average y1 plus y2 over 2. And similarly, θ2 hat is y1 minus y2 over 2. Okay, right? If you subtract that, 2 θ2 is what you get, divide by 2. Now you see the variance of θ1 hat, θ1 double hat is variance of the average. Now here is something I'm not going to prove. Its variance of an average is 1/2 of the variance of an individual observation. So it turns out variance of this θ1 double hat is variance of this y1 plus y2 over 2, and that is exactly sigma square over 2. What happened? Variance is half as much as the variance of the earlier estimate that I got for θ1. Similarly, variance of θ2 hat is also sigma square over 2. So the point is, By a clever scheme like this, where I take the sum of the weights and the difference of the two weights, I paid $100 for that measurement, $100 for this measurement, same cost as before, but I got much more precise estimates. This estimate is smaller variance. These estimates have half as much error as those under method 1. Or to achieve the same precision, method 1 requires twice as many observations as method 2. So if I take 2 measurements on x1, 2 measurements on x2 on the method 1, I'll get this precision sigma square over 2 by averaging. So this is a very simple idea. You would think if you have 2 objects, 2 measurements are allowed, you would take the first weight and the second weight separately like I did in method 1 and declare and go home. But I'm saying statisticians have something called a theory of optimal designs. See my blue letters here. This is this whole idea. When you have some job like this, what is the job? You want to estimate theta 1 and theta 2. And what is a good way to do this? How to design a method for getting such theta 1, theta 2 estimates. And this is, there's a whole subject called theory of optimal designs. Everything I mentioned has a book or dozens of books sometimes on this topic. In fact, I have a book that we recently published. It's called Linear Models and Regression with R. Linear Models and Regression with R. It's a 750-page volume. We just came out last, what is it? We are in 2019, 2020 still. Yeah, it came out this year. So, and there's a section on theory of optimal designs. How do you optimize? What do you mean by design? This is a design. To get theta 1, theta 2, I'm saying take the sum and the difference. And there's a certain weights that go with theta 1 and theta 2. And that's called a design matrix and so on. So this is the point I wanted to make is in this example 1, there's an excursion that you took you to, and to what's called theory of optimal designs. 2 objects, you can do twice as good with method 2 as method 1. So there is such a thing as when you do an experiment, you have to ask yourself, what is a good way to do this? For example, when you do linear regression models, xi, yi, you collect data. If you have the choice to fix where the xi's can be, they are the inputs and the yi is the yield or whatever, how should you pick these x1, x2, xn? Okay, x is the amount of fertilizer you put, y is the yield that you get resulting on the x. So the question is, if you can choose how much to experiment using different amounts of fertilizer x1, x2, xn, how should you fit these x1, x2, xn to get good estimates of the slope and intercept and the regression? So those kind of things are called optimal designs. Okay, here is another example 2, another excursion for you, which is it's called randomized response surveys. A usual opinion poll or survey would have innocuous questions like, in the coming election, would you vote for Mr. T? T was Trump at one point, but anyways, okay. In the coming election, would you vote for Mr. T? And then if 92 people answer yes out of 200 people, suppose this is the example, for example, and then you say 92 out of 200, 46% of the vote is going to be obtained by this Mr. T. Right? You're all familiar with this. This is how we do opinion polls. And then a confidence statement would say he has, this T, has 0.46 plus or minus 2 times P times 1 minus P over N. What is that about? 2 is 1.96 approximation. So this is how we get a confidence band, 95% confidence, right? This is something you teach in the 3rd or 4th week of elementary statistics course. Proportions, how to estimate a true proportion with a sample, and then how to set a confidence interval for the estimated proportion. Now, this is what you do if I have what I call an innocuous question, simple question. Are you going to vote for Mr. T or not vote for Mr. T? Okay, so then this is what happens. But if you have sensitive questions, the survey is about sensitive questions like, did you use illicit drugs during the last 2 years? Well, you want to do a survey like this? How many people will agree that they did? You're not likely to get correct responses. Most answers will be wrong or incorrect to avoid getting caught. So what is this goal that you have? Your goal is to find out what proportion of people use drugs. In fact, I did such a survey in a neighborhood of the university campus in Santa Barbara some long time back. And I helped the people do a survey like this. I don't myself go around doing this. But so if you want to get an answer to a question like this in red, did you use illicit drugs during the last 2 years? You're not going to get a correct answers. So how do you, this is what I call a sensitive question. Or maybe did you have an abortion anytime? Or did you cheat on taxes during the last 3 years? Well, nobody's going to tell you, that they did cheat on taxes, right? Even if they did. So these are the kind of things what I call sensitive questions for which I want an answer by survey. Or even such a question like, how much money do you make? People won't hesitate. They won't give you an exact answer. So I'll tell you tricks for doing this. So what you do is, this is where we use, okay, I don't know what's going on. My slides are getting hidden there. Did you use drugs? Okay, the question one, I'm going to make up two questions. What is the first question? The question of interest to me. Did you use illicit drugs during the last 2 years? Okay, and the question, true proportion is pi 1, let's say, which we really want to figure out. What proportion is the people use drugs? Pi 1 is the number. That is the number I want to find out. And then I make up a fake question, question 2, which says, does your telephone number end with an even digit? Okay, I make up this question. This is a innocuous question, nothing special about it. And the true proportion, say pi 2, is known. Say 50% of the numbers, telephone numbers, end with 0.0, even digits, and 50% of the odd digits. So I know the answer to this question, question 2, the proportion is pi 2. What am I doing? I have two questions, although question 1 is the only one of interest to me. Did you use drugs? Question 2, I make up. I want to get this pi 1, which I don't know. Pi 2, I know is approximately 0.5. So prepare a deck of 10 cards, say, 4 of them write question 1, 6 of them with question 2. Okay, 10 cards, 4 of them will, I'm just making up some examples for you. 4 cards will have question 1, did you use drugs? 6 of them will have this question 2. And then each respondent selects a card at random and answers yes or no. Here is what I do. I give these 10 cards to the person that I want to interview. What 10 cards? 4 cards with question 1, 6 cards with question 2. I ask them, shuffle all you want, these 10 cards. Shuffle them thoroughly, randomly, and pick a random card, any card out of the 10, and then say yes or no to the question that you selected. And then they will say yes or no. And we don't know to which question they said yes or no, because they picked the random question. And even if they saw the question 1, they can confidently say yes, because you can't pin them down. Maybe they were saying yes to this question too. So this protects their identity or their confidentiality. Did you have an abortion? Question 1 might say that, and they might say yes or no, and then this is similar. Okay, so this is what 4 and 6, and these 10 cards are given to them. They shuffle, they pick a question at random, and they answer. And we don't know whether they said yes or no to which question. That's why it's called a randomized response survey. Randomized response. The response you're getting is randomized. How do you get the pi 1? What is the pi 1? Pi 1 is the true answer I'm seeking. Suppose I get 92 out of 200 say yes. I'm just making up numbers again. So probability of yes is 92 out of 200. And now here is a small probability. It's called a compound probability. Probability of an yes answer is yes given question 1 times the proportion of question 1. P stands for probability. Probability of yes to question 2 given, that's a given question 2, times the probability of question 2. What does this remind you of? This is what, for example, if somebody gets an A grade, is it a girl? How many girls? This is the P, Q1 may stand for girls in the class, and yes is A grade, and this is boys and proportion of boys. So what total proportion of A grades is proportion of A grades out of girls, proportion of girls. So this is a standard combination of yes answers can come out of this yes or that yes. So you see, now I know in this formula, I know this is 92 out of 100, let's say yes, and pi 1 is 0.4. Why 0.4? Sorry, P of Q, question 1 is 0.4, because 4 out of 10 questions are of question 1. So 40% of the time they select question 1. Probability of question 1 is 0.4. Probability of question 2 is 0.6. Probability of yes on question 2 is 0.5. What is this? Does your telephone number end with an even number, even digit? And so I know everything here except for pi 1. So it's all done. So if both pi 1 and pi 2 are unknown, 2 surveys are needed, and this is called randomized response surveys. And I had a student who did on the following topic. Let's see, I am going back too far back. So how much money do you make? If you want to do a survey on this, you do the following. You take 10 cards, write numbers 1, 2, 3, up to 10. 10 cards, write numbers this time. Number 1 on one card, number 2 on the second card, number 3 on the third card, and give these cards to the person that you want to interview. Ask him or her to shuffle these cards completely, pick a card at random, and maybe they get 6. And then multiply your income by 6. Multiply how much money do you make? Whatever money you make, you multiply by that random number that you picked. And then from these numbers, I can estimate not that particular person's income, but the income distribution. I had a student did a master's thesis on this kind of topic. So random multiple of your actual income is what you get reported. And then how do you find the distribution of the income, the actual incomes? Okay, so that's called a randomized response surveys. Now, how am I doing on time? Should I wrap up in under 10 minutes, 15 minutes? Okay, I'll carry on until I finish. I think I'm almost done. Okay, this is my example 3. I have 4 examples altogether, 4 excursions for you. So one was that thing about the first example where, so-called designs and optimal designs and so on. And the example 2 is randomized response surveys. Example 3 is something called factorial designs. You see, oftentimes there is a factorial design is where you say, yes? Is there a question?
No, sir.
Okay, I'll carry on for another 10, 15 minutes. Okay. Okay, here is what happens. Factor 1, say temperature. Factor 2, say the percentage of carbon you're trying to make steel, good steel. You add carbon into iron ore and so on. So low or high, low or high. There are 4 possible combinations. And your goal is you have been assigned, you are working for a metallurgy factory, and they're asking you to find out, should you put low temperature and high carbon? Or what is the good combination? And then typically what do people do is what's called 1 factor at a time. What is 1 factor at a time? You start with factor 1. Go with low and high. Factor 1, temperature. Say temperature, low temperature, high carbon, low carbon. And then you say, oh, 64 is higher. So you stick with this low, this one, and then run this experiment that way. And then you still say 64 is the best one. Are you with me? So are you, for example, you start with this experiment, you go with this and you say, here 64 is the best one. You do run this experiment with using that combination, and then you get. So what happened is you missed this 68, which is this higher than all the other numbers. This is called a interaction effect. Low versus low declared best combination with 4 measurements. What are the 4 measurements? Factor 1 you ran with two experiments, and factor 2, second time you use this one and then ran again 2 experiments. So this interaction effect is ignored. This is not a good way to go. This is versus factorial experiments. What is a factorial experiment? You run all the 4 combinations at one time. And then you find out a full factorial experiment measures all combinations of the levels, all low with the rest of low, low with H with H, all these combinations. And estimates then, again with 4 measurements only. But estimates are twice as accurate. I won't get into that. You can show that the estimate of the so-called main effects are twice as accurate as the one factor at a time. Arrives at the right conclusion in the first place. If you do all 4, you obviously catch this guy. And then what happens is when the number of factors is not just 2, but many, then it turns out if you have 10 factors, each at 2 levels, there are 2 to the power 10 combinations of treatments. Let me repeat. If you have 10 factors, each at 2 levels, low, high, let's say simple. I'm making life simple. So then there are 2 times 2 times 2, 2 to the power 10 possible combinations of treatments. So there is something called a fractional factorials. So you don't have to deal with all the 2 to the power 10, but only a certain fraction of this. So this is called fractional factorial experiments at the base of a revolutionary quality control methodology called Taguchi methods. I don't know if some of you teach SQC methods, or anyway, Taguchi methods are very well-known methods. Taguchi, incidentally, was at the ISI Calcutta for a time way back in the 50s, and then that's early 60s maybe, and then he picked up these ideas of fractional factorials, and he became very popular for this. Okay. Now, finally, my last example for this. This is my favorite, one of my favorite topics. This is called directional data. I think I could have done something better, but maybe I don't want to fool around now. Okay, so what is this about directional data? You are measuring directions. So for example, which way is the wind blowing? Suppose the wind is blowing in this direction. See this arrow here. Question, how do you measure this number? This is what we call north, this we call east, that's fine. But what is that number? What number do you assign to that? If you're a mathematician, you go this way and say 60 degrees. If you're a geologist, as I often talk to geologists, they say true north is what should be called 0. They call it an azimuth. And they go this way, anti-clockwise. Sorry. I forgot where the clock was, clockwise. They go clockwise this way. So they call it 30 degrees. Coming that way, going 0 to 360 like so is 60 degrees. Starting there and going this way is 30 degrees. So should you call it 60 or 30? Value depends on the choice of origin and sense of rotation. What I mean by sense of rotation is clockwise or anti-clockwise. And more interestingly, if you have 2 birds, say, flying in these 2 directions, this you're a mathematician, this is your 0. You release 2 birds and they fly in this direction, 15-degree direction, and 345-degree direction. Someone asks you, what's the average direction of the flight of these 2 birds? So immediately grab your calculator and add 15 and 345 and divide by 2. And you end up with 180. And you say, that's the average direction. Completely wrong. 180 degrees wrong. right? So what's happening is, when it comes to directional data, there are several problems. One problem is, you have to measure, which way you measure should not make a difference. 60 or 30, whether you call, when you do inference for this, you should not make different kinds of conclusions for someone who goes this way or someone who comes that way. So this is called invariance. Okay, and then similarly, the zero direction should not make a difference. This is obviously is a wrong thing to take the average. Sample mean, the arithmetic mean points the wrong way. Arithmetic mean is the averaging, adding and dividing. So, for instance, treat the angular data as unit vectors pointing in the specific directions and obtain the resultant vector of such vectors. This is a tutorial on a topic. So if this is one bird's flight alpha 1, and this is another bird's flight alpha 2, think of this as a vector of length 1. This is another vector of length 1. Take the resultant vector. As the R is the resultant vector. And then the direction of the resultant vector is the average of these two numbers. And that will never go wrong, no matter where the zero is. And then the length of the resultant vector is also a useful tool as to how close alpha and alpha 2 are. If alpha and alpha 2 are overlapping with each other, this will be very long, length 2. If alpha and alpha 2 go in opposite directions, its length will be 0. So the length of the resultant vector you certain measurements. Okay, that's my fourth excursion for you. I'm almost wrapping up. I'm concluding by saying statistics everywhere, data mining and business analytics. That you guys have courses on data analysis, data analytics, actuarial and financial models. We have, I should perhaps quickly throw in a word. I started a department of statistics some 25 years back. We have 1,500 undergraduate students, 1,500 undergraduate students and then about 80 or so master's and PhD students. And we have actuarial statistics as one of the disciplines we teach. Insurance mathematics, life tables, and so on. And financial models, we teach share prices and option prices and so on. So we have about 400, 500 students doing that, undergraduate majors, and there are 500 students doing this, and another 500 doing the regular statistical undergraduate degree. And text analysis, I briefly told you about it. Text analysis is how do you analyze a text if it's similar to another text. Image analysis, retinal detachment. These are all topics I worked on. Optical coherence tomography. And you have to talk to, I don't have the time to even explain what this is. Retinal detachment is when you're getting older and you sneeze very hard, apparently your retina detaches itself from where it's supposed to be attached to nerves. And the question is, how do you treat it? So we had done experiments with cat's eyes and how do the data that generates from, this kind of detachment after 15 days, detachment after 30 days. Statistics everywhere is the title on the top there. So optical coherence tomography, there is a L.V. Prasad Eye Institute in Hyderabad. I'm sure you heard of it, L.V. Prasad Eye Institute. What they did, they are studying people who come in and they draw pictures about the retinal images. It's called optical coherence tomography. If you have the time, look up what this is. And we are trying to find out data curves around a circle, and then trying to figure out how, whether someone might be getting a, glaucoma or not getting a glaucoma, things like that. Microtubule dynamicity and Alzheimer's. We are dealing with this Alzheimer's patients and how the, inside your cell, In the body, there are billions of cells, and in this cell itself, there are microtubules, tubules that you can only see with electron microscopes. And how dynamic are they? These tubes are growing, and we are trying to find out how fast they are growing and so on. So these are all interesting topics and research topics for my students and so on. Need for statistical help for those doing research in any substantive field. What we did in Santa Barbara, before I started the Department of Statistics, I started a statistical consulting lab. I called it a statistical consulting lab or stat lab. So all these students, graduate students and faculty would flow and say, I have this problem. Okay, what data, what analysis should I do and so on. So maybe there's a scope for starting some kind of a help center for helping people with statistics. Okay, there's my last slide there. And these are some of the references, just a couple of them, but the most important one is at the end. What is this reference? This is a book I wrote with a professor at ISI. It's called Topics in Circular Statistics, the last topic. And there is a paper I just recently published in the Proceeding of Indian Academy of Sciences. It's called A Matter of Direction. It gives you a lot of examples where directional measurements come in. And we developed an R package called CircStats, Circular Statistics, doing much of this type of statistical analysis. It's freely available online on R package. So these days, R is a freebie that you can download, and this you can do. These three are about the last topic. And here is something that you perhaps might want to note down. It's a free book that I wrote called Essential Statistics with Python and R. Essential Statistics. I wrote this book long time back. It was used as a textbook for beginning undergraduate students, and it's basic stuff. Essential Statistics is what I called it. More recently, I added Python and R, how to learn Python and R. And it's a free book you can download by going to the website. Can be downloaded. Free is the word, important word. Can be downloaded if you go to this website and say download the PDF. And it's called https://escholarship.org. UC is University of California, item. And I don't know if these slides are available to you later on, but if they are. Okay, I'm going to stop there, and I'm going to stop my share, and I'm going to stop here and see if you have any quick questions or comments. I see some chat here, but I don't know if I'm supposed to. Now, Shweta, is she still around? Let's see. What am I? Okay, I still see. What is this chat? Okay, well, I see you are responding to. Oh, thank you. I think chat is oftentimes asking questions of me, but okay. I just try to give you some overview of different topics in statistics that maybe one of you will get excited about and get interested. And I'll stop here. Is someone going to conclude this session, or do I conclude it myself? Hello?
Dear participants, if you have any doubts, you can unmute yourself and clarify your doubts with the sir.
Hello, good morning, sir. My name is Johnson. Hello, am I audible, sir?
Yes, say it a bit louder.
Yeah. Is it audible, sir?
Yes.
So my name is Johnson Samuel. I work in a health department. We have a huge data. I have a thought to use statistics in the work what I do. Actually, I was asking some of the people who are from the medical sector. They were saying that community medicine is one of the topic you can use for the statistics based analysis. So can you recommend any books so that we can use at our level? I work for the state level, state of Telangana. I work in a health department.
Uh-huh.
I'm a data manager for National Health Mission.
I see. Yeah.
So just yeah, because we have a huge data. The thing is that we need a proper guidance to how to
Yeah.
based on the subject point of view, like based on the
Yeah.
disease point of view.
Yeah, this is very important. This is what I was mentioning in my last part, namely that I started a statistical consulting lab, and we help students and the faculty and people with questions like yours. And I don't know what a resource is that in Hyderabad, for example. I knew, for example, Usmania University. There are these universities. Maybe the local people might be able to give you some lead as to where such consulting facilities might be. But book-wise, if you this baby statistics book that I recommended, then you might download and take a look at some of the basic ideas like what is a linear regression, what is a t-test, what is f-test, things like that are in my book, that essential statistics. Um, but overall, yeah, I can't tell you specifically. If you know what you might do, I don't want to get myself into this loop, but if you tell me a typical problem that you are trying to solve and send it to me, uh, I can perhaps tell you a reference at least, if not a book to look at. Hello, did you get me? Okay, anyone else?
Thank you, sir, for such an enlightening and informative lecture. I'm sure that you all the participants have a wonderful time learning and exchanging the thoughts. Let's call upon Mrs. Jayashree, Statistics Coordinator, to propose vote of thanks.
Thank you, ma'am. It gives me an immense pleasure to deliver the vote of thanks for this one-week international online faculty development program on mathematics and statistics to all dignitaries assembled here. First of all, I thank today's eminent speaker, Professor Srinivasa Rao Jamal Madaka, University of California, United States of America, for accepting our invitation in spite of his busy schedule and grace this occasion with his inspirational talk. My sincere thanks to Professor Mutyam Reddy sir, Secretary Hyderabad Mahila Vidya Sangam, Professor Sudarshan Reddy sir, Secretary cum Correspondent, our beloved Principal, Dr. Achyuta Devi ma'am, and Head Department of Mathematics and Statistics, Shweta Srivastav ma'am, for their valuable contribution, guidance, encouragement, and continuous support in organizing such college events. I thank to ICT committee for giving technical support in organizing a program. I thank all the distinguished participants and my dear colleagues for your active participation. Thank you all.
Thank you. Yeah.
Thank you, ma'am. I request all the participants to join tomorrow meeting at 2 p.m. Sir, ISB Hyderabad. Thank you, sir.
Thank you. Goodbye, everyone. Goodbye.
Okay, the recording stopped.